fascinating, right on the cutting edge of science where we're at today. Killing zombies. Most of the diseases that make people miserable as we age and end up contributing to our demise, inflammatory, lifestyle-related, age-related diseases. And science has now discovered that there is a common pathway to many of these age-related diseases, whether it's arthritis or dementia, heart disease, many of these metabolic diseases, dysfunctional diseases. As we get older, nothing works the same in range, are actually related to zombies, zombie cells in our body. And so we're going to take a look at that there. I think all of us know what cells are in our body, the billions and billions of little teeny intricate units, muscle cells, brain cells, skin cells, liver cells, every kind of cell. Each one has its own job, and they all work together to create your human body and carry on all of its functions. Well, tonight we're going to use what the scientists refer to as senescent cells. There's a big word for you. Senescent. It comes from the same root as senile. These are old cells that aren't working right anymore. A senescent cell starts off as a normal muscle cell or brain cell or epithelial cell or whatever. But because of damage, whether it is radiation damage, chemotherapy damage, just what we call genetic damage. Every time your cells divide, they get some genetic damage on them. Oxidative stress, junk food in our lifestyle. All of these various things impinge on cells and damage, weaken them. And there comes a point where these cells, they change. The cells age and they become what we call senescent. They're old senile cells and they don't do what that cell used to do. If it's a fibroblast cell, it doesn't keep making collagen and build up your connective tissue. And so on. All of these cells, they don't do what they're supposed to, but they don't die. They stay there. But they're transformed into a zombie, the living dead, and they will kill you. Zombie cells, they don't do what they're supposed to, but they start putting out chemicals into the body, to the cells around them. They transform cells around them. They bring on inflammation. They can cause other cells to turn into cancer cells. We realize now that these zombie cells are really at the root of much of what we would call age-related diseases, age-related changes in your body. Even the change of hair colors, you get gray hair when you do this. Zombie cells down in the roots of your hairs. Zombies there. So tonight we're going to take a close look at these senescent cells, these zombie cells, and they will get you. And we're going to talk about how to kill the zombie cells and how to get rid of them. That's one of the exciting things that science is now discovering. There are ways to kill zombie cells. And we're going to talk about that and give you some pointers on how to get rid of your zombie cells so you don't have to suffer from their attacks in your body. Let's take a look at how the zombie cell. is a normal cell, young, healthy cell doing whatever it's supposed to do. And here, that cell has aged and become a senescent cell. And there's going to be a number of changes here. The cells tend to enlarge a little bit. The nucleus enlarges, and the chromatin, the genetic material in the size here, it changes its shape and structure there and function, and it's not doing the same things it used to do. The mitochondria, the energy source of your cell, they start to become dysfunctional, and they don't do what they used to do. And the cells stop making the substances they used to make, and other things start building up in the senescent cell here. Lipofuscin is a substance that builds up there quite a bit, and as it builds up in there, it makes the cells, we come up and see it, it's stainable here, and we can see the cells better and tell, so we can look into the microscope and say, oh, there's a senescent cell. But the really bad thing is these cells, they stop doing what they were supposed to do, but they start making something they shouldn't be making. And this cell is starting to make a whole set of hormones, cytokines, chemokines, various proteins, metalloproteases, all kinds of things here that they secrete out into the area around the cell. These things tend to lock the cell into its senescent state, but they start affecting other cells around it. And as they affect the other cells around it, that's how they bring on the damaging effects. Here's a picture. These are actually normal fibroblast cells. They're the ones that make the collagen in your connective tissue and kind of what holds everything together in your body. And here is the fibroblasts, several of them here, that have become senescent. Notice the lipofuscin is built up here. There's a number of other proteins that are building up in here. The energy levels go down in the cell, but they're not dead. They're still alive, they're still functioning. But now, instead of making collagen fibers and elastic fibers and various other things that your connective tissue needs, and secreting the things that are needed for the matrix around there, they stop doing all of that, and they start secreting all of these inflammatory chemicals. There's cancer-causing chemicals, there's growth factor chemicals that can bring just a huge lot of bad stuff going on there that they're doing. Notice they tend to look larger. They tend to swell up, get large, they kind of flatten out compared to their normal structure. So these are your zombies. You know, one or two zombies isn't going to be too much problem. But when you start getting, 15, 20, 30% zombie cells, you're going to definitely have dysfunctional tissue. You're going to have the problems of inflammation and the diseases associated with inflammation, deterioration of the other cells around them, and in many cases, formation of cancers in those areas right there. Here is a senescent cell. This cell has become senescent. There's a little listing up here. We can see some of the substances which have helped to make our senescent cell go into this state. Seems to be a normal part of aging, and yet it's not really normal. This really shouldn't happen, but it does. Chemotherapy drugs, very powerful at disrupting internal function in the cell and can push a cell into senescence very rapidly. Many people who have taken chemotherapy can attest to how damaging chemotherapy is to every part of your body when you take it there. Closely related to that over here, radiation, whether it's from some type of nuclear fallout or X-rays or some therapeutic radiation for a cancer. Radiation damages DNA structure right here. You know, we have all of these genes in our DNA to do everything possible that a cell can do. And the way you make a cell do what it's supposed to do is you turn off the genes you don't want functioning right now and you turn on the ones you do. And so that's how the cell works. Well, in these senescent cells, something went wrong here and we end up switching off most of the very important functions that cell was supposed to do, and instead we turn on some other very dysfunctional things. And so the cell sort of converts into this very dysfunctional thing that's putting out all of these, secreting all of these things that are affecting the cells around it. One of the things right here, they talk about replicating stress. You know, all the cells in your body, they go through a process called mitosis. And they divide and they separate into two cells because they duplicate. All of the chromosomes get duplicated. Now you end up with two cells, all with the same genetic material and chromosome there. When they do that, they take with them all of the switches, and so, you know, what was switched on is switched on, what was switched off was switched off. And, but each time they divide, the ends of these chromosomes, they call them telomeres, but there's little things on the end which start damaged. They're like little just repetitive things on the end, but some gets clipped off and gets clipped off a little more. And when the telomeres get short enough, they can't divide anymore because they need those telomeres out there, something in the process. They need those little telomeres on the chromosomes to do that. And once you start clipping a lot of those off, again, with aging, these cells have divided so many times during your lifetime, they can stop doing that. We have a process in the body where there is stem cells that can come out and repopulate an area with new chromosomes, and you can kind of start that process over again with healthy stem cells. But in this case, these are the product of the cells that have made up those tissues, and as they divide and divide and divide, they get closer and closer to slipping over the brink from being a normal cell into being a senescent cell. So this replicative DNA damage can be part of it here. What they call oncogenic signaling. Cancer cells make certain things that go out of them. There are certain genetic things on their oncogenes, genes that can cause cancers, things. And turning on the wrong genes, switching on the wrong switches there can push a cell over here. And of course, what are the different things that do it there? Just plain old stress, cellular stress, whether it's, temperature, various chemicals, various food substances, all of those can stress the cell and push it into dysfunctional condition here. And of course, oxidative stress. We've often talked about the importance of antioxidants. Part of life, part of cellular function is the cell creates these, we often call them reactive oxygen species. They're an oxidative substance. An oxidative substance is damaging, it's dangerous, it can hurt cells, and it can damage and cause stuff here. And of course, the more antioxidants we have, the more we can put out these fires before they spread. And so, a diet high in antioxidants can be protective here, avoiding drugs and radiation here. And of course, aging, well, we don't know quite what was in the tree of life, but anyway, we age, and that just plain replicated stress can push us over into senescent cells here. And of course, once we get into this senescent state right here, the ability of a cell to divide and to make two new cells stops in the senescent cell. It's like an irreversible switch. You flip that switch, and that cell becomes senescent and it won't divide anymore. Senescent cells don't go through mitosis. mitosis and dividing. It's like their useful lifespan is over, but like the zombies, the living dead, they don't die. They continue to live in those tissues, they continue to take in a certain amount of nutrients, and they produce these inflammatory compounds here. SASP, senescence-associated secretory phenotype, is what the scientists use it here. This is sort of a name for this whole group of substances. It's not just one substance they put out, it's a whole group of substances here. There are certain growth factors, endothelial growth factors, other growth factors. Now these are important in formation of cancers. You know, our body often has a cell that mutates and becomes cancerous and it starts dividing. But a cancer can't divide much bigger than a dot the size of the end of a ballpoint pen. The little tip of the ballpoint pen that you write with. That's about as big as a cancer can get on its own. You start multiplying this ball of cells, pretty soon the ball of cells is big enough that you can't get enough oxygen or nutrients to the cells in the middle, and so it starts dying off. So you can't get bigger than a teeny dot like that without building a blood supply. In other words, the tumor has to start building blood vessels into it to do that. And here is where the senescent cells pushes over into that cancer. With these growth factors that it puts out, these little cancers that might have been forming and weren't bigger than a dot and can't get bigger than a dot, which really isn't going to hurt you, now they can grow blood vessels. And those blood vessels, now it's got a blood supply. We've opened up the road, we build roads in there, and we start bringing in oxygen and nutrients and amino acids, and these cells can thrive and grow and grow and grow as they continue to grow this. And it's these senescent cells that make that possible by putting out all these growth factors right here. You know, cancers with age become more likely and more frequent and more commonplace. And that's exactly what we're seeing here. And it's these growth factors that do it. Cytokines. Cytokines are little communicator molecules that communicate inflammation. They go to a cell and the cytokine hits it, it flips it into an inflammatory mode. And if you think about the role that inflammation plays in diseases now, it's really quite extensive. The inflammation, you know, arthritis, osteoarthritis, these painful inflamed joints, that's inflammation. The joints are inflamed and the immune system is all modulated and out of control and attacking the joint. It gets swollen, it gets red, and it gets extremely painful. And it gets so bad that it starts remodeling and the bone remodels and you can just totally tear down the joints till they're non-functional. You can go in and try to replace them with an artificial joint, but it's an inflammatory process that is driving that, and here is the source of the inflammation. It's these senescent cells in that particular tissue are putting it out to the cells around them. And of course, some of these things, these chemokines and these different things, they can all start actually pushing other cells around them to become senescent cells. They can do the type of aging, damaging to a cell with inflammation that can do that. Atherosclerosis, hardening of the arteries. You know, we all know it's related to certain things in the diet, our typical American diet that's making it that way, but inflammation is a key factor in there now. Doctors today, when they're looking at you to see it, they'll do a test called C-reactive protein, CRP. That's an inflammatory marker of how much inflammation. And if there's not another cause of inflammation, they'll assume that's coming from the artery walls. The little myocytes, the little muscle cells in the artery wall that allow it, those can become inflamed. Endothelial cells can become inflamed. But it's the myocytes down in the artery wall. They become senescent, they become inflamed, they start pushing out inflammation around them, others can become inflamed. And of course, all of our oxidative stress, all of the French fries we had, you know, with all of their oxidative stuff comes in and gets picked up. It starts building up into this area right here. The macrophages, the cells that come in to start cleaning up the mess, they become inflamed, over hyperreactive, they turn into these big foam cells. And it's these senescent cells that are actually helping and pushing and driving that process along and worsening it with all of their various inflammatory cytokines. A big issue today is neurodegenerative disorders. We think of most neurodegenerative disorders as diseases of aging, and rightly so, they are. And this seems to be that. It's the microglia. You know, in your brain, besides the neuron, there's supporting cells around them, astrocytes, glias, and microglia. And these microglia are the cells which frequently become senescent in the brain. And as the microglia become senescent, they become hyperinflamed. They put out a lot of inflammatory stuff and inflame the other microglia around them, and they can actually drive the other microglia into becoming senescent as well. And it progresses. We find inside the microglia in the brain various things that we find in Alzheimer's disease, this tau protein and these neurofibrillary tangles, and all of these things that we see as part of Alzheimer's, we're seeing them in these senescent cells. It's these zombie cells, these cells that are no longer should be alive, but they're still alive, but now they're just zombies, you know. Here's a zombie cell here. Notice how wide and enlarged it is. The nucleus is quite enlarged. The DNA material in the center is breaking down. All of this other stuff is building up in here, which you wouldn't see in a normal cell there. In the secretory, all of the stuff that you see these little things sticking out, it's actually these little feet-like things pulling out, and they break off and release the secretory substances out into the fluid around them. It then goes into receptors and starts triggering the cells next to them. It can trigger them to become cancer cells. One of the things that comes out of here is something that can start breaking down the boundaries. You know, every tissue and organ in your body has walls and edges and boundaries. They're structurally things that hold it together and keep the cells that are part of it in there and parts that aren't of it out of there. Well, for a cancer, even if it's growing, to become really bad, it has to become metastatic. And you've got to break down that barrier, and so the cell can get free and go and move out on its own somewhere. And to become metastatic, you need these senescent cells breaking down those boundaries with these various substances that they are secreting. Here you can see the diagram we looked at earlier here. Notice it's building up all of these extra secretory substances here, and they're being released out. See it kind of bubbling up here and coming out, being released here in the little panties out here, and this will affect and can go out and reach other cells there. Same as these little things sticking out here in the picture there. And of course, senescence-associated secretory profile. This is the name that they use to describe. It's sort of the lump name for these dozens and dozens of different factors that these zombie cells put out. Here's again a list of them. And this is just a brief list of some of the categories of them. There's actually more of them. They keep studying these senescent cells, and they'll find new ones, and this one does this, and this one does this. You know, but it's all bad stuff that you really don't want going on. And when you start building up more and more senescent cells, your body is older and older. Older in the sense of becoming more diseased and breaking down. Aging, cancer, arthritis, dementia we talked about. The more of these zombies you got in your body, the sicker and more miserable you get. So, How do we kill the zombies? You know, the movies and TV is full of zombie movies, and you got to go out and kill the zombies. I've never quite figured out how the dead, you could kill them again. You know, it's like they've been dead from all these things, and then you go out and you shoot them, well, now they're dead. But anyway, that's how the movies work. But the zombies, these cells that should be dead and they keep living, is the real problem. So how do we kill them? Well, to understand that, first of all, we need to understand something else. Now, this cell right here is not a zombie cell. No, this is not a zombie cell. This is to help us understand how to kill zombies. This cell is undergoing a process called apoptosis. There's a big word for you, apoptosis. What is apoptosis? Apoptosis is a process by which a cell kills itself. We sometimes use the term cellular suicide, or sometimes we call it programmed cell death. So these are the terms right here, apoptosis. It's a very specific biological process. And it's different than just a normal, what happens to a cell when you die. You know, you can kill cells. All the cells in your body die when you die. They don't undergo apoptosis. They undergo necrosis. Necrosis, if you get an infarct, if you get gangrene, if part of your body dies, that's not apoptosis, that's necrosis. The blood supply is cut off, there's no oxygen to it, or you burn it in fire and heat it too hot and the cells die. The cells just disintegrate. Necrosis and apoptosis are totally different. Apoptosis is actually a very programmed process that goes on in that cell. There are switches that you can turn on in a cell, and when you turn them on to reach a certain point, get them on, that cell will destroy itself in a very organized, methodical way. We do it normally during embryonic development. To turn from a little blob here into a human being, you end up destroying a lot of in-between steps. I mean, just think of a hand. If you've ever seen a picture of an embryo, as a hand starts to develop, there's just a little bud, and then it kind of grows out like a little arm. But what the hand is just sort of a little blob. And you start to see finger rays forming in that blob, but then the fingers separate. Well, what happened to all those cells in between? Apoptosis. And so with the forming of the organs and the dividing of your body into all these different organs and tissues and systems, apoptosis to the in-between stages and steps as we develop the more, you know, think of it as a sculptor undergoes, you know, you get a block of marble and he chisels away at it till what he wants is left. And that's development. And so apoptosis is very much a part of new living life. And it's also plays a role here. Here is another picture here. Here's a cell, normal cell. And now this cell is starting apoptosis. First it starts making these little bubbled out knob-like things. Those knob-like things will turn out to longer projections. And at the same time, there's enzymes inside that start cutting up and tearing up the other thing. The cell stops doing its normal things, makes proteins whose job is to cut up and destroy and get everything ready for recycling. And eventually, it will go back to that last picture there. Here you can see it here. It's and now it's starting to disintegrate and come apart into all these little ball-like pieces right here, which will be devoured by macrophages. You know, those phagocytic cells, the ones that eat and swallow up and gobble up various debris, whether it's bacteria or viruses or any other debris, digest them up, turn them back into their basic materials so they can be recycled in the body. Well, the macrophages will come and clean up all of this debris from an apoptotic cell. And once this process starts, you can't reverse it. You know, it's like, you ever seen one of these science fiction movies and suddenly somebody self-destruct button and all the lights are flashing, beep, 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 you know, will self-destruct in so many minutes and everybody's rushing to abandon ship. I never considered why they would build such a system in a spaceship, but you know, it's the movies they do. But that's sort of what happens in here. Once you flip the switch and this cell gets the message, this apoptosis, you can't really reverse it. It's going to go ahead and it starts going through these various scenarios. It starts chopping up all the things, chops up the membrane, chops up the DNA, chops up the stuff. It goes through several steps right there, and it gets everything packaged and ready for recycling. Here's a little more diagrammatic picture of apoptosis. You've got a regular cell, but as the proteins, it stops making the other one, starts making the apoptotic proteins, and it starts chopping up stuff here, starts breaking it up. And you start getting these little blebs like bubbling out on the surface here. As it progresses, those blebs get bigger and more prominent. You notice here the nuclear material is chopped up in pieces here already. And the other organs in there, the Golgi apparatus, the endoplasmic reticulum, all of these end up in little blebs and vacuoles and pieces in there. And these little blebs out here starting bigger here. You'll see the blebs, and look, some of them are even stretching out from these little spikes or filaments. And the material's all wrapped in various pieces of membrane. See all the little balls and pieces in there. And you know, it's not just randomly put in pieces there, it's actually organized. You'll find some of those little vacuoles will have DNA pieces in them. Another one has RNA pieces in it. Another one has, lipoprotein pieces. Another one will have proteins for recycling. And all of these things, it's sort of like a recycling center, and everything is being packaged and sorted into cans so that when the macrophage comes to gobble everything up, he's already got it packaged and sorted. And so he's got a package of DNA here. Well, he can add to that package of DNA exactly what he needs to chop up DNA into the individual nucleic acids. And once you get down to just down the individual nucleic acids, then those can be released out into the cytosol. Other cells can pick them up and use them to build DNA or RNA or whatever they need. And so with all the other recycled pieces. So it's a very organized process. It's designed not to waste materials, but it's designed to get rid of a cell that's no longer needed. It's not needed for a purpose, whether it's in embryonic development or whatever cell that we don't need, we can do it. Notice some of these spikes as they develop out here, these little tubule pieces right here, here's kind of large. They start getting a little knobby looking, almost a beaded appearance, and those beads can actually separate and break off as little balls. Here's the final thing here of cell fragmentation. You see it just all beaded up and coming apart, and there's just all of these little debris. And of course the macrophages, the phagocytes, they come in and just swallow up, devour up all this stuff and recycle and reprocess it. When here's an apoptotic cell right here. See, it's breaking up into the little pieces here. It secretes out substance, little chemical markers that are actually signals to the macrophage here, telling it, come find me, I'm over here, got something for you to recycle here. And as the message goes over there, it moves, it's attracted to it, goes right over to it because of these signals it's sending out, and goes over to it. And when it gets there, he finds the surface of it, is covered with these other little signals that say, eat me. They're like, if you want to call it, little candy coated. It's flavor. It says, that's good, that's what I want to eat. And it has removed all of the don't eat me signals. You know, your cells in your body have these don't eat me signals. I'm an important cell. I have a job to do here. Little markers on it. So if a phagocyte comes up to that cell and starts to touch it, touches one of those, it says, leave that one alone, and it won't devour it or eat it. But in its process of getting ready to that, it removes all of those don't eat me signals and replaces them with eat me signals. And so this comes in, and it just, here you can see the phagocyte just devouring the cell with all of the little vacuoles that have broken off of it there. And in the process, it's producing anti-inflammatory cytokines. There's different kinds of cytokines. They control inflammation. There are certain ones that cause inflammation and certain ones that say stop inflammation. And so here we've got, they say, no inflammation here. Let's calm down. Everything's under control. We've cleaned up this mess. There was a cell here. He went apoptotic and devoured, and we're going. This is actually a picture here. This is a macrophage. And look up here. See all these little different balls in there? Those are all parts of an apoptotic cell that is devoured. All those little pieces there. And notice they're all different. Each one has its own recycled components in here. Now, this isn't a random process, but we won't go through each of these in detail. But when you do something this drastic as apoptosis, you know, self-destruct of the entire spaceship, you know, right here, you don't want to make a mistake and do apoptosis that you don't. And scientists have been studying apoptosis now for quite a while, and they actually understand most of the key players in apoptosis here. And as you can see, it's a very complex process with many different steps feeding into it and feeding out of it, you know. And there's many steps to turn on. But there comes a point, you go far enough down this cascade, it's the point of no return. It's sort of, it flips the switch. We're going apoptotic. You can't reverse it. It's going apoptosis now. And the mitochondria, there's a lot of factors that they are involved with here as they disintegrate. There is these cuspin proteins, these kind of pink ones here. They're the ones that go around and start chopping up membranes. Here's a nuclear membrane here, it gets chopped up. The DNA gets fragmented here. All of these things get fragmented. The endoplasmic reticulum will start wrapping up these pieces. It's just a complex process, and it takes all of these controls doing their part to effect it. It's really a very major process, a very controlled process, and anyway, that's the story. That is a magnificent picture of an apoptotic cell. This is the spaceship that's undergoing full disintegration here. You see the blood's forming, the little tubules forming out here. This is what we want to do to those senescent cells. Those senescent cells should never have been there. They should have undergone apoptosis right at the beginning. And that brings us up to the exciting thing today is something called senolytics, substances that kill senescent cells. In other words, what the exciting thing today is they have found there are certain drugs, substances, chemicals, they can take these senescent cells, put them in there, and they can flip on apoptosis. They can actually turn on apoptosis and target the senescent cells and not the healthy cells. And they've done it in mice, reversing these degenerative aging type changes and actually extending the lifespan. And when I was looking at 36% longer life with destroying the senescent cells by various senolytic agents. There's dozens and dozens of human trials going on right now where they're trying to come up with different drugs to do this. One here, it's actually a chemotherapy agent. Sprycel is used to kill certain types of cancers, to push them into apoptosis. This is actually a picture of a cancer cell here that's been pushed into apoptosis. See, it's starting to blood out, and you know, you heard people that they go on healthy diet, whatever, and their cancer disappeared. And something turned on apoptosis in their cancer. Well, here they're trying to do it with a certain drug here, this chemotherapy. Turn on apoptosis there, and here is the macrophages coming in. They've got that come find me, come eat me signal, and they're coming in to try to devour and clean up this cancer cell. That's one of the ones they're using. Chemotherapy drugs have a lot of side effects, so you know, we don't know where these trials will go. Another one they've found right here, this one, many of you have probably tried this one, zithromycin, a common antibiotic today. We sometimes get it in what they call a Z-pack for a sore throat or something. The Zithromax is actually a powerful. Look at the structure of it. You notice like they have a lot of those ring structures in there. A zithromycin, here it is. Clicker's dead. The zithromycin down there is the one that selectively, you put a thing, kills 97% of the senescent cells and doesn't touch the normal cells. This roxithromycin, very similar structure. It kills all the senescent cells, but it kills a bunch of good cells too. You know, we don't want to start doing apoptosis and that stuff. Erythromycin, another very closely related one, does nothing to either one. Doesn't hurt the zombies and doesn't hurt the good cells. So not much hope there. Another one they're using, quercetin. Now you might be familiar with that name. This is a substance found in nature. It's found in many fruits, vegetables, and foods. And here it is. You can see the apoptotic cells there starting to fill up. It'll take senescent cells and push them into apoptosis. And they're using that in some of their trials right now. Where could you get some quercetin? Apples is an excellent source of quercetin. There's a lot of quercetin in apples. You know the phrase, an apple a day? Well, this there. Your bright colored berries, your dark green leafies are high in quercetin. And radish greens, for some reason, have a lot of quercetin. But the highest of... but the highest of all, where you the most quercetin, goji berries. For some reason, goji berries are high in quercetin. And the highest of all, over 200 micrograms in a spoonful, capers. You know what capers are? They use them as a seasoning, sometimes in Italian foods or something. It's they're the buds of a plant. You cut the buds off before they flower, and they usually pack them in brine, so they're a little salty. You can rinse the salt off if you didn't want that much salt. But throwing some capers in really throws the quercetin in there. Here's something interesting. Tomatoes have quercetin. And if you take what you're familiar with, your greenhouse-grown tomatoes with all the usual production goes in, packed, and then sold in the store. Well, they compared the quercetin content in that with organic tomatoes. You know, this is your homegrown garden ones without any pesticides and artificial chemicals and stuff. And you know what they found? 80% more quercetin in the organic grown tomatoes than in the the routine ones you get at the store.
Is it good green tomatoes or red tomatoes?
The red tomatoes, most of these things we're talking about are actually pigments that actually help add to the color of it. They're not the only things that color, but they're part of what's adding to the color there. Yeah. So yeah, the brighter red, the ripe fruit that's fully colored, fully vine ripened, that's where you're going to really load up on the quercetin. Hopefully you had a garden at home this year and have been picking tomatoes all summer and been loading up on those.
You don't have to eat tomatoes, green tomatoes fried. They're delicious in salads.
Here's another one, ficin. Notice the structure very similar to that quercetin structure. Another natural substance found in plants that is a powerful senolytic, bringing on the apoptosis of senescent cells without affecting the other cells. Where would you find ficin? Grapes, you could get 4 micrograms in every gram. Onions, 5. Persimmons, double that at 11. Apples, again, apple a day, 27 micrograms. But there is one winner. So the apples are at 27. Guess what's in this next one? The highest source of ficin. Strawberries, 190 micrograms per gram. You know, in the spring when the little strawberry stands are open, I like to go around every few days and get one of those big flats of strawberries and bring it home and make it into a strawberry smoothies and drink them down. It's like spring cleaning, you know, for your tissues. You know, you just flood it with this ficin, get rid of the senescent cells, and restore the tissue back to a normal, healthful baseline function rather the inflammatory function. You know, so many times, if you talk to anyone about this, what? Eat lots of fruits, eat lots of vegetables, and you'll be healthier. And here's probably one of the reasons why. Because in these fruits and vegetables, all these is exactly what we need to clean out the senescent cells. This is how we kill the zombies and get them out of there so we can have normal functioning tissues and instead of inflamed arthritic tissues and, you know, inflamed microglia and dementias and destruction of the neurons and the memory cells and all that. Of course, anything good, people will want to take advantage of here, and guess what? You can buy bottles of quercetin and ficin at the store to take if you want. Before you do that, though, I'd like to suggest something else. You know, quercetin and ficin are just one of hundreds of polyphenol molecules. There is your